Hello, friends. Welcome to Science Talk. I'm your host, Jim Assa. I want to discuss with you what this headline is: the NOAA Annual Greenhouse Gas Index, or AGGI. And this is something that's been in the works for a couple of years, and it's now starting to become more commonplace. And I actually think it's a really good idea, and we'll go through this. So you see, NOAA Global Monitoring Laboratory, located in Boulder, Colorado. These are the gentlemen who are overseeing this program. So what is AGGI all about? Okay, here's a summary of its purpose. Let's just go through that. The AGGI is a measure of the climate warming influence of long-lived trace gases in the atmosphere and how that influence has changed since the onset of the Industrial Revolution. The index was designed to enhance the connection between scientists and society by providing a normalized standard that can be easily understood and followed. The warming influence of long-lived greenhouse gases is well understood by scientists and has been reported by NOAA through a range of national and international assessments. Nevertheless, the language of sciences often eludes policymakers, educators, and the general public. This index is designed to help bridge that gap. The AGGI provides a way for the warming influence to be presented as a simple index, just basically a number with no units attached to it. Now, oftentimes, it happens all the time. The way we're taught and trained to how to write out papers is that there's a certain language that we use, and because we're communicating our findings, our research with our colleagues, so we understand what we're saying. But you take that same language and you present it to the public, and oftentimes it's like, what the hell are you guys saying? So it really, there's kind of a gap there. And in the old days, we just publish a paper. You publish a paper. Now there are scientists who are now understanding the need to be able to explain their research in terms that the average person, the non-scientific, the non-professional scientist can understand. For example, I've been showing you some videos lately where I show you the abstract, and it's very wonky and all technical and stuff like that. And then underneath it, you see what? Plain language summary. It's a nod to that, the fact that there is oftentimes the language that us scientists use is not always transferable to the general public. But there are some scientists, and let's face it, this is what I'm trying to do with this channel here. I'm trying to present the information in a ways that are understandable. Now, some of you have requested that I cover some of the scientific papers with you, and I'm doing that. And I think you can start appreciating how wonky they can be. Putting that aside, I think this is a really brilliant idea, and it presents a number. And if you understand what the number means, then you can understand the information being conveyed. So let's quickly go through the introduction here. Increases in the abundance of atmospheric greenhouse gases since the Industrial Revolution are mainly the result of human activity, largely responsible for the observed increases in global temperature, based on IPCC 2014. Because climate projections have large model uncertainties that overwhelm the uncertainties in greenhouse gas measurements, we present here an observationally based index that is proportional to the change in the direct warming influence since the onset of the Industrial Revolution, also known as climate forcing, that is supplied from these gases. So what they're saying here is that there are some parameters that have large uncertainties, And those uncertainties can overwhelm the uncertainties of some greenhouse gas measurements. In other words, you can cause the signal of these greenhouse gas measurements, for which we have good measurements for, to be lost, to be overshadowed, etc. It's what we call confounding errors, basically. Now, in physics, when we talk about forcing, we're talking about the effect a parameter has on whatever outcome, whatever variable you are taking under consideration. For example, changing in the tilt of the Earth's axis will create forcing in how heat is absorbed on the surface of the planet and distributed. Right? That's a forcing. Okay? You have tidal advection forcing. How does that influence the mixing and how organisms are, say, for example, plankton are distributed? So in physics, forcing means something that's causing an effect, some sort of process. Okay? So this index is based on the observed amounts of long-lived greenhouse gases in the atmosphere, which contains little uncertainty. Okay, so the IPCC defines climate forcing as an externally imposed, put it right there in quote, externally imposed perturbation in the radiative energy budget of the Earth climate system. For example, through changes in solar radiation, changes in Earth albedo, changes in atmospheric gases, and aerosol particles. Part of my research in looking at sea ice and surface currents in the Arctic Ocean was I was conducting heat budgets. Okay, thus climate forcing is a change in the status quo, forcing changes in the climate. IPCC takes the pre-industrial era, chosen as the year 1750, as the baseline. Some may argue 1800 is more representative. We'll discuss that in a moment. For what they calculated here, they used 1750. They did calculate the forcings using 1800, and their finding was that there really was the differences were very slight and not significant at all. Perturbation to direct climate forcing, also termed radiative forcing, radiative when heat radiates off a body, that has the largest magnitude, the smallest scientific uncertainty, is the forcing related to changes in the atmospheric global abundance of the long-lived, well-mixed greenhouse gases, CO2, right? Carbon dioxide, methane, CH4, nitrous oxide, N2O, and various halogenated compounds, the CFCs. I'm going to be concentrating and looking at these three here in this video presentation. Keep in mind that this, along with this tab up here, I will include the URLs for those tabs in the comment section below in the video. Measured global atmospheric abundances of greenhouse gases are used to calculate changes in radiative forcing beginning in 1979 when NOAA's global air sampling network expanded significantly. In other words, that allowed for improved measurements of gases, a wider spread of measuring the gases, in other words, measuring and sampling a larger and larger region. The equipment's improved, the measuring improved. In other words, the errors reduced. The change in annual average total radiative forcing by all the long-lived greenhouse gases since pre-industrial era is also used to define the AGGI, the NOAA Annual Greenhouse Gas Index, which was introduced in 2006 based on measurements through 2004. That's the Hoffman et al. Paper they're citing there. So here are the observations. Surface discrete in the red, observatories and so on. Blue is from aircraft flying about. So they were collecting all these measurements from all over the planet, best they could. And they describe, they got weekly data and so on. So when you can pull this link up, you can go through the information in greater detail. And you can then pull up this URL to look further. But some interesting things to note here. CO2 has increased by an average of 1.85 parts per million per year over the past 41 years, 79 to 2020. This increase in CO2 is accelerating, right? While it averaged about 1.6 parts per million per year in the 80s and 1.5 parts per million in the 90s, the growth rate increased to 2.4 parts per million per year during the last decade, 09 to 2020. The annual CO2 increase just in the past year alone, from 1 January 2020 to 1 January 2021, was 2.5 plus or minus 0.08 ppms. Growth rate of methane declined from 83 until 99, consistent with its concentration approaching steady state. But since 07, methane has been increasing again. Causes of the increase not yet fully understood, but warm temperatures in the Arctic, translation, permafrost thawing, in 07, increased precipitation in the tropics during 07 and 08 contributed. In the early years, isotopic measurements argue for continued increased microbial emissions after 08, likely from wetlands, likely from agriculture such as rice paddies, likely from microbial action in the permafrost. Since 2015, the global annual increase in methane become even larger, averaging 9.7 plus or minus 3.3 parts per billion, and the YR with the -1 exponent, that's per year. So parts per billion per year through 2020 compared to the average annual increase of 6.4 plus or minus 2.9 parts per billion per year between 08 and 2014. The annual methane increase in 2020 was 15.85 plus or minus 0.47 ppb, parts per billion, which is the largest annual increase recorded since 83. I think part of that is most likely due to all that methane coming off the East Siberian Arctic shelf, the Laptev Sea, in other words, what's going on in the Arctic Ocean. The atmospheric burden of nitrous oxide continues to grow over time. The annual increase in nitrous oxide atmospheric burden, averaging 1.0 parts per billion per year over the past decade, is also increasing. The annual increase in 2020 was the largest recorded since measurements began. Are we sensing a pattern here? Radiative forcing from the sum of observed CFC changes caused increasing in about 2000 and has continued to decline ever since, which is a response to the global controls placed on CFC production due to the ozone hole issue. So here we see the CO2 increasing. Here's the methane. Here's that little decline, and then it started increasing again. Here's the nitrous oxide, and here are the two major species of CFC, and we can see the decline due to regulations. Now we get to the calculations. Okay. To determine the total radiative forcing of the greenhouse gases for the AGGI, we've used IPCC recommended expressions to convert changes in greenhouse gas global abundance relative to 1750 to instantaneous radiative forcing. And they refer you to Table 1, which is this right here. In a separate analysis, and you can click on that to look at it, we use 1800 as the base year and have added additional gases, but this had little effect on the trend or the amount of radiative forcing, or in other words, the calculated delta F that I'll explain to you in a moment. These empirical expressions, in other words, these formulas we see here, are derived from atmospheric radiative transfer models, generally have an uncertainty of about 10%. By contrast, uncertainties in the measured global average abundance of long-lived greenhouse gases are much smaller, less than 1%. just in case I caused a little confusion, and I apologize for that. Much smaller, the less than 1%, refers to these formulas here. The 10% is a result of trying to figure out what's going on to the water vapor, ozone depletion, as well as aerosols. Now, other spatially heterogeneous, short-lived climate forcing agents such as aerosol, tropospheric ozone, highly variable, have large uncertain global magnitude. So there's where the large errors are introduced, resulting in this 10% uncertainty that they expressed up here. So for purposes of their calculations, they have not considered those. They've considered those parameters that they got very good, very accurate, very reliable measurements from, leading to very little errors. So here are the equations. I will explain this at the end of the video, where I actually take you through some sample calculations. There's some constants in here: alpha, beta, epsilon, omega, and with the value all derived from calculating, from looking at the models. They explain what n sub 0, m sub 0, c sub 0 are. They define some of these functions here, and then they give you the values of the c sub 0, m sub 0, n sub 0. 278 parts per million, 722 parts per billion, 270 parts per billion. That's 1750 levels. Okay. Because we seek an index that is accurate, only direct forcing from these gases have been included. Model-dependent feedback, for example, water vapor, ozone depletion, aerosols, are not included because of the uncertainty. Water vapor is a very difficult parameter to work with. And then to show you the results. Figure 3 shows radiative forcing for CO2, CH4, N2O, and other gases that capture changes predominantly, right, for the CFCs and so on. CO2 is by far the largest contributor to total forcing from these gases, and with methane and CFCs following. So this blue color here is CO2. This lighter blue, I guess, is methane. This pink, or is it magenta, whatever, that's N2O. And then you have the CFCs in yellow and so on. So they start from 1979, because why 1979? Because as stated above here, that's, where was that? That's where they started to get really good data. So they were confident in the data that's collected. And then they do a reference here to 1990 with the value of 1. So let's look on the left side here. Radiative forcing is in units of watts per square meter. So you calculate that. And you add these all up. So you calculate the radiative forcing for carbon dioxide, for methane, nitrous oxide, the CFC. You add it all up and you get the total radiative forcing. Then, to calculate the AGGI, you take whatever you calculated for the year and you divide it by the total radiative forcing for 1990. And that gives you your index, your AGGI index. So why 1990? Why that year? 1990 was the year that the Kyoto Protocol was agreed to. In other words, when we're going to start actually trying to do something about global warming. So when you look at this here, the AGGI for 2020 is calculated as 1.47. In other words, if you compare this total radiative forcing over in watts per square meter to the value calculated in 1990, and you divide those out, you get 1.47. Since 1 is the 1990 is the standard that has a value of 1, that means in the 30 years since, radiative forcing has increased by 47%. In other words, radiative forcing is how much warmer, how many more watts per square meter on the surface has been increased, has been added. Okay. So radiative forcing relative to 1750, that's the left side. The NOAA AGGI is indexed for year 1 to the 1990 because of the Kyoto Protocol. That's on the right side. And then they talk about CFCs. The atmospheric abundance and radiative forcing of the three main long-lived greenhouse gases continue to increase, while the combined radiative forcing of these and all the other long-lived, well-mixed greenhouse gases included in the AGGI rose 47% from 1990 to 2020 by about 1.02 watts per square meter. CO2 has accounted for about 80% of this increase, approximately 0.82 watts per square meter, making it the biggest contributor to increases in climate forcing. In other words, climate heating since 1990. So, if you look at this here, if you calculate the total area of everything you see here, right, then calculate the total area for this blue color that indicates CO2, this accounts for about 80% of the total area. You can do simple integration, upper curve minus lower curve, use your limits of integration, and so on, figure out what the functions are, or you can subtract out the areas, whatever, the number of technique, but you can easily calculate this. So you can then calculate the how much each of these gases contribute to the total forcing in watts per square meter. You can also do it by looking at the tables, which I will share with you in a moment. And the rest of this chapter to talk about CFCs, as I said, you can click on the link and read that. My concentration is going to be on CO2, CH4, N2O. This is an important one right here. The annual greenhouse gas index, AGGI, is calculated as the ratio of total direct radiative forcing due to these gases in a given year to its total in 1990. 1990 was chosen as the baseline year because of the Kyoto Protocol and the publication year of the first IPCC scientific assessment of climate change. Most of this increase is related to CO2. For 2020, the AGGI was 1.47, representing an increase in total direct radiative forcing of 47%. In other words, of the warming. And they discuss how, they got, the atmospheric measurements and so on. I want to show you this figure right here. The AGGI is the red line. The light blue line is just CO2 alone. This dashed line, at 1, you drop it down, that's 1990. So there's that Kyoto Protocol. The black line is basically CO2 and everything else combined. What to take note of is what? Exponentiation, right? This thing is exponentiating. Like everything else, like the rate of warming, the rate of ice melt, the rate of permafrost thawing, everything is exponentiating. Okay, some of the measurements for the gas levels were collected by analyzing the air trapped in ice and snow in glaciers and so forth. Now, this table here, this table goes from 1979, the start of getting really good, the deployment of really good instruments, more widespread, starting to get more accurate and so on. And then they measure the CO2, the CH4, the NTO, and all these other here, and then they add these all up. Then they calculate a CO2 equivalent. Now, take the ppms or the ppbs, whatever the case may be, and then you make it equivalent to CO2 and you sum it up. So right now we talk about, we've got 421 parts per million of CO2, But the CO2 equivalent is about 580, 590. That means when you look at the contributions from nitrous oxide and methane and some trace gases, for example, the CFCs and so forth, when you convert that into an equivalent, in other words, this methane would be equivalent to this amount of CO2 warming. And then you combine it all together. Because don't forget, methane oxidizes down into CO2. So don't forget that. So let me zoom down to 2020, right? You have these values here. If you add these up, you get 3.183. That's the total, right? That's this right here. That's that value right there off the chart. The total radiative forcing in watts per square meter. That's how much the heat per square meter has changed. So I could take 2.111 divided by 3.183 to get that approximately 80% of the CO2 contribution to this total. And then you can do the same thing for the other species. Here's that 1.47 AGGI index. So, gives you a general idea of things. Let me click over here. And we can show you the trends. Let's see. Let's go to that tab there. Global monthly mean. So here they're showing from 2017 to 2021. And you can see the seasonality being reflected, and you smooth that out. And this takes it down to 1980. And you can see the unmistakable trend that it's increasing. And, the dashed red line, they describe in detail what the figures are. The red here is the seasonality. The black is the fitted curve. That's basically what's going on there. And you can do this for CH4, right? Do that there. And again, they're doing the last 4 years and then further back in time. You can do the same for nitrous oxide, except here they go 20 years back, 4 years back. But in all these cases, we see the increase. Now, the methane, of course, we see this little slowing down, leveling off, decline before it ramps up again. I did a video where I hypothesized, and I don't know if anyone's done the study, that this decline or leveling off might be due to the mad cow situation, where a lot of cattle and livestock was slaughtered. So those animals basically, their flatulence contains methane. That's my hypothesis. I don't know if that is correct or not, but that's what I'm thinking. And then you have trends in sulfur hexafluoride. That's what SF6 is. Right? Sulfur hexafluoride. And again, it's increasing. So I will include these two URLs. You can, poke around on here and explore. But what I want to do, though, is I want to show you this animation. Now, this animation is really kind of cool. What it does is, okay, it got blocked out here, but this on the far left here, that's 90 degrees south. That's the South Pole going up to the North Pole. And this red dot is 1979, 336 parts per million measured at Mauna Loa. So the red dot is Mauna Loa. The blue dot's the South Pole. And when you watch this here, you'll watch the values creep up over time with some spikes. But what's really interesting is what happens on the right side of this graph. It takes it from the last 40 years, but the graph works its way back until 800,000 years ago. And you'll see it written as KY. KY is kilo years or 1,000 years ago. So you'll see it written like that on the horizontal graph. and it twirls around through the years, and it goes up to 2019, I believe. So this is a really interesting graphics, and so let's let it rip. You see how it's waving up, and then you see the seasonalities going on here, and at the same time, they're fitting the curve. You notice how it just keeps creeping up. Up to 89, up to 90. Now it's starting to see some extra spikes there. Look, see that? And see, it's really spiking. And we're still in the 20th century. Still the 20th century. 21st century now. It keeps getting higher and higher. And look what's going on the right side. Keeps increasing. October 89, Mauna Loa records 350 for the last time. You see how it keeps climbing higher and higher. Now we're over 400. So in January 2019, it's at 411. 2 years later, we're at 421. Okay, now watch. Now take a look at the right side. Look what's going on. Right, going back to 1960. And now they're taking you back to, medieval dark age time. Let me pause it right here for a moment. Look at that. See the spike? That spike there. And that spike starts about there. There's your 1750 or so. Okay, let's let it continue. Going further back in time. 20,000, 25,000 years before current era. 80,000, 100,000. 250. And there you have it. But now look at this here, okay? You see the cyclical aspect of these, right? So this is low CO2 levels. These are higher CO2 levels. When the CO2 levels are low, we have a ice age. We have ice sheets. When it's higher, we have the interglacial. The ice sheets melt back. So about, that looks like about what, 300,000 years ago or so, it got to 300 ppms. Otherwise, it's been pretty much below 300. And now, wham, in the last basically 100 and about 70 years, it's jacked up to well over 410, almost up to 420 or so. So this kind of shows you, what humans have done in such a short time. And don't forget, I just did a video where I discussed with you how only 7% of the greenhouse gas that the humans have emitted into the atmosphere have stayed in the atmosphere. The other 93% has gone into the oceans. And now the oceans are stratifying. So all that heat energy is waiting to diffuse back into the atmosphere. That's thermal inertia, folks. Okay. So as I said, you can, I'll include these two URLs. So what I want to do now is I'm going to want to take you through some sample calculations. So let's pull this guy up. And I'm of the firm opinion that do not just dump numbers into computers and so on, unless you know what the hell you're doing. In other words, unless you're able to calculate yourself by hand the values. Now, the other thing is, when scientists, publish papers, we're communicating with our colleagues, but we're also doing what? We're basically saying, here's how we did things. In other words, we share our methodology, we share formulas, calculations, what have you. The whole point is that if another researcher wanted to verify or recreate what you did, they should be able to. Okay? So I wanted to be able to reproduce, calculate for myself to verify the values given in that table that I showed you. Now, once I do this for a couple of them, then I understand how the functions work, this and the other thing. And once you don't have to do it for the whole lot of them by hand, that's silly. But you should be able to do it for a few of them so that you understand what the functions are doing. And that's what I've done here. Now, if you have computer programming skills or you're good with the spreadsheets, whatever, you can then write the appropriate formulas, write the appropriate programming, get that up and running, enter in the table of data and, have that as a file, read that file in and just let it crank. That's fine. But to me, it's important to understand how things were arrived. So here's some sample calculations. General functions. To estimate the change in forcing, defined as delta F for CO2, delta F is equal to alpha times the log of C divided by the baseline carbon level in 1750. Okay. For methane, delta F is beta times. Now, when you see something raised to a fraction, that's usually involving a radical. So m raised to the 1/2 power, that's basically take the square root of m. Okay? M stands for methane level. M sub 0 stands for the methane level in 1750, the initial. So take the square root of the current methane minus the square root of the 1750 methane level, and then subtract from it this formulation. We have F, M, and N sub 0, F of M sub 0, N sub 0. Now, this is a function based on two independent variables, methane levels, nitrous oxide levels. Okay? Alpha and beta are model-derived constants with no units. Here are the given values that they arrived at. And then C sub 0, M sub 0, N sub 0 baseline concentration based on 1750 for carbon dioxide, methane, nitrous oxide, respectively. And here are those values. Values to calculate delta F is via the graphs that discussed earlier in the video. So I start out with the simple one. The delta F the change in forcing for carbon dioxide for year 2020. Carbon level is 412. C sub 0 is 278. Now I'm using their values that they reported. Okay? So you dump the 412 in and divide by 278. So you do that division first, take the log of that, multiply by 5.35, and you get approximately 2.11 watts per square meter, which, there it is, 2.11. So it agrees with that. Okay. Now for methane. For the year 2020, we need to define what is meant by a function of M and N. Well, the function of M and N is given by this equation. 0.47 times the log of this mess. So you got 1 plus 2.01 times 10 to the minus 5 times the product of M times N raised to the 0.75 or the 3/4 power. So what is the 3/4 power? That means whatever the number is, you take the fourth root of it, then cube that result. Okay? So going back up to here, if I had something that's raised to the 1/3 power, you take in the cube root of it. If I have something raised to the 2/3 power, take the cube root of it, then square it. For example, take 64 and raise it to the 2/3 power. Okay, the cube root of 64 is 4. I square it, I get 16. And something like that. So that's what that is. Okay, continuing on, we then add to that 5.31 times 10 to the minus 15 times m times n. This product raised to the 1.52 power. Okay, brief word about how to do these calculations in the correct sequence. We have PEMDAS, P for parentheses, E for exponents, MD for multiply divide. The same thing. When you divide by something, you multiply by the reciprocal. So, 32 divided by 2. Well, it's 32 times 1 half. Okay. And then AS, add, subtract. So what you do first is you do stuff inside the parentheses and you work your way from the inside out, because we got a whole bunch of groupings of parentheses and brackets. So I multiply the m and these values together first. Okay, I've done that. I then exponent, so I raise it to that power. I then multiply by the m, and then multiply by these guys. So I'll multiply it out. I do the same procedure here. Multiply these two, raise it to that power, multiply by all this. So I get a number here. I get a number here. I then add up 1 plus that number, and I get a bracket in there. I then take the log of whatever that mess is, multiply by 0.47. It's tedious, but it's also very simple and straightforward. But again, you should be able to verify the numbers for yourself. So for methane, delta F is equal to beta times the square root of m minus the square root of the m time t equals 0. And so what I did was, because I have to run this mess of a calculation several times, have to perform it here, have to perform it here for different values. So I broke it down into I and II. And then we just put the pieces together. Okay, so let's do this first one here. Beta, okay, beta will be given as 0.036. There it is. The value for methane in 2020 was 1880 parts per billion. Take the square root of that. M sub 0, 722. So take the square root of that, subtract from the square root of that, multiply by 0.36. Again, do the stuff inside the parentheses first. I get 0.593601. Okay. Now for this one here. M is going to be 1880. N sub 0 is 270. Okay. 1 plus 2.05 times. Now, this is another way to write 10 to the something. I just didn't want to write little exponent, little tiny numbers there. I want you to be able to see it. When you see the letter E, capital E, that means 10, and then raised to whatever the number follows it. If you were to see in capitals EXP, that means exponentiate. In other words, E to whatever follows. That's how it used to be. That's how we used to write it in papers before we were able to have word processors that did things like subscripts and superscripts and all that kind of stuff. So I'm just plugging and chugging the numbers in, right? 1880, right? So on. 1880 again, 1880, 270. So I multiply these two. I raise it to that power. I then multiply by 2.01 times 10 to the minus 5. I get that number there. I set it aside. I go over here. I multiply 1880, 270. Raise it to this power. Take that result, multiply by 1880. Multiply by 5.31 10 to the minus 15. I get that number. I have it here. I have this number here. I add that. I add 1 to it. I take the log of that. And I multiply by 0.47. And I get this result. What you don't want to do is, you do not want to multiply these three numbers, then raise it to that power. Or worse yet, multiply everything here and then raise it to that power. You get an erroneous value. If this bracket was way over here, then that's what you would do. But the bracket is saying, no, we're going to do this stuff first, multiply that, then raise it to that power. Then continue with that multiplication. So I get that value. Okay, so that's for this one here. Now for M sub 0, N sub 0, I do the same thing, except now I replace the 1880 with 722. The 270 stays the same. So I crank that all in, follow the same procedure I just described, and I get this value. 1 minus 2. Okay, now let me scroll that up a bit. Okay. 1 minus 2, I get this value, and now I subtract that from the beta, as from above, and I get 0.520396 or 0.5204, which 0.520, they did 3 decimals, they put a 4th decimal, you have the 4 there. So the value agrees. Okay. So what we're doing here is, when you look at this, we're basically, when you have multiple, more than one independent variable, what we're doing is we're treating one variable as a constant and then vary the other variable. And as I will show you, when we calculate for N2O, we'll switch. We'll treat the other variable as a constant and then change, and so on. So in this one here, we're treating the nitrous oxide value, 1750, as a constant, and we're varying the methane levels. When we do the nitrous oxide, the methane will be the constant, and the nitrous oxide level will vary. So for 2020, I use 1880. If I wanted to calculate the radiative forcing for 2010, I would go to the 2010 charts, to the graph there, read off the value for 2010, whatever the value is. I would then plug it into this equation. This second one, in essence, becomes a constant. So all I have to do is plug in the value there, recalculate that, and then I would still subtract this value from it. And I can do that for all the years. So this is one of those things where I have to set up a loop of like, okay, change the variable here if I was programming this, and then just keep referencing this number. So we got the value that agrees in the table. So the radiative force and change in F is about 0.52 watts per square meter for methane in 2020. And then I say F of M sub 0, N sub 0 will be the same value as is based on baseline values for 1750. The only value that changes is M, which gives us the delta F for methane. And then if we're calculating for nitrous oxide, then N would be the only one that changes to give us the delta F for nitrous oxide. And a little reminder of PEMDAS. Parentheses, exponent, multiply, divide, add, subtract, left to right. Okay. Nitrous oxide for the year 2020. General formula. Okay, epsilon, square root of n minus the square root of n sub 0. And now you notice it's m sub 0 n. Still got the same m0 n sub 0 here, function of that. Right? Compare it to this here. Seeing how we have the n sub 0 and the m. This is the same. F of that, so on. Now we just simply have f of m sub 0 and n. Okay, going to do the same thing, break it up in pieces, right? We calculate a function of m and n as before. That's that gnarly formula. For 2020, n is 333 parts per billion off the graph, 270 for n sub 0, 722 for m sub 0. So epsilon times the square root of 333 minus the square root of 270. Do that, subtract, multiply, you get that value. Piece 1, f of m sub 0 n is 722, 333. Same formulas, and we just use different values now. We plug and chug, and we get 0.93,004. Part 2 is the same as before. We just calculated that. Right? They're the same as before. 0.80531. No sense repeating it. That's a constant now. So we just carry it through. Right? So part 1 minus part 2, we get those values, and then we subtract this value from that 0.217993, and we get about 0.206 watts per square meter, and there it is, 0.206 watts per square meter. Okay. To calculate delta F of methane, we use the values of methane from the graph. We hold the nitrous oxide values as constant. And then to calculate delta F for nitrous oxide, right, we use the values of nitrous oxide from the graph, but we hold methane constant, vice versa, and use the baseline values for 2 for all calculations. That 0, 8, etc. I showed you. It's similar thing like the density of seawater is dependent on temperature and salinity, 2 independent variables. So if I wanted to calculate the rate of change in density with respect to temperature, I'm going to treat salinity levels as constant and the temperature changes. If I want to calculate the change in density with respect to salinity, I hold temperature as constant and I look at changes in salinity. And then we get what's called a partial derivative. If you're interested in, I did a video on salinity where I explain all about partial derivatives and so forth. Check out that video, plus the information on what salinity is. Very important in the ocean. Okay, now for the AGGI. These 3 lines here means defined as the ratio of total forcing for all gases in year whatever divided by the total forcing for all gases in 1990, Kyoto Protocol implementation. So in 2020, delta F of T is 3.183 watts per square meter. 1990 is 2.166 watts per square meter. Okay, there's that 3.183 for 1990. Excuse me, 2020. And 1990 is the 2.166 right there. So that's where they're getting the values from. And again, you get these from summing these up. Okay, overshoot there. Okay, so watts per square meter, right? 3.183 watts per square meter, 2.166 watts per square meter. Notice how I include the units. I am a big proponent of including units in your calculations. It's one way to check to see if your results make sense because you look at your units. Do the units work out? If not, then your setup is incorrect. So using units is a great way to check your work. So the units cancel. You do this division and get that 1.47, which, there it is. So you notice it is a value that has no dimensions. But we can look at this and say, well, 1.47 is greater than 1, which is the 1990 level. So therefore, there's that increase of 47% in the forcing, in the radiative forcing, which is basically how much warming, extra warming per square meter has occurred. In other words, if I look at a square meter in 1990 and I look at it in 2020, that square meter has now 47% more heat. That's what that's telling you. That's a lot when you think about it. 47% more heat over 30 years. And you can do this for any of the years. So I really like this this method. It's simple, straightforward, easy to understand. So if I look at 2018, okay, that means the warming has increased by 43%, 32% in 2012. So there you have it. I said I think this is a very good index. I think it will be extremely useful, very handy, and it's something that the non-professional scientist or the interested layperson can easily understand and get their minds around the concept. So I hope you found this informative. I said I will put the URLs for these 2 in the comments section, so look for it there. You can click on it and explore the information presented there in more detail at your leisure. So once again, I hope you found this informative and interesting, and I thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.